Ryan is the head of Google's quantum algorithms team, he's part of the quantum group over there. And he's done seminal work over the years that's led to the development of the first first post-Trotter quantum simulation methods for chemistry, as well as he's pioneered methods for simulating chemistry in a plane wave basis. And also recently has spent a lot of time developing first quantized simulation methods, which we're going to hear a lot about right now. So take it away, Ryan.
All right, great. Thank you, Nathan. Yeah, so today I'm going to try to sort of convince you of the fact that I believe the sort of long-term future of quantum algorithms for chemistry is ultimately to focus on first quantized approaches, and that in that regard, it's quite different from most correlated methods that we focus on classically. So this talk is going to be a little bit of a funny talk. Most of it, I would say, will be sort of review material and material that I wasn't even necessarily involved in. But towards the end, I'll talk about some more recent work, although it's still work from a couple years ago for the most part. But I think work that, in my opinion, has maybe been a little bit underappreciated. So I felt like I should still talk about it here. Okay, so mostly at this conference, we're talking about simulating molecular systems. And of course, molecular systems have a Hamiltonian that look like this. It involves interactions of electron and nuclei. And in full generality, we would like to treat the nuclei quantum mechanically as well. But often we focus on simulations in the Born-Oppenheimer approximation, where the concept of an energy surface is sort of well defined, and we're just focusing on computing the energy of electrons and the external potential of the nuclei. And this is, sort of appropriate in situations where you can consider the nuclei as being classical, for example, at high temperatures, or if you have heavier nuclei involved in the reactions. But there are also a lot of contexts where non-Born-Oppenheimer simulations are important. For example, low temperatures, or when, hydrogen bonding is involved, you might have tunneling, or when there's conical intersections, you might have non-adiabatic effects, coupling between the electrons and nuclei. And you also, in general, you might want to compute dynamics. You might want to compute, reactive scattering coefficients or, thermal rate constants directly from quantum dynamics. And I should point out that you're not going to be able to use molecular orbitals for true quantum dynamics because those are centered on nuclei. And if the nuclei are moving, that just doesn't really work. So I'm going to argue throughout this talk that whenever you're sort of outside the Born-Oppenheimer approximation, or if you really want to seek very high precision, I think that the most compelling way forward on a quantum computer is to use a very simple first quantized discretizations. So using grids or plane waves or something like this. So I'm going to spend a couple slides here just reviewing something as basic as the difference between first and second quantization, although I think many are familiar with this. The way I think about it, in second quantization, when we're simulating quantum chemistry, the computational basis states on the quantum computer, they are just product states. They're not antisymmetric. They're just computational basis states. But they are meant to encode spatial wave functions that do have special symmetries. So, for example, a computational basis state might correspond to a Slater determinant. And because we're implicitly encoding the symmetries in this way, whenever we operate on the wave functions, we have to remember that. And so the operators have to sort of keep track of the symmetries. And this is, for example, why we require that these fermionic operators satisfy certain anti-commutation relations. And that's where mappings like Jordan-Wigner or Bravik-Shayev, something like that, are coming from. In contrast, in first quantization, the quantum computer states have to explicitly have the same symmetries as the simulated system. I should say the first paper that was simulating chemistry in first quantization is this one from Casal and Zbrogusic and others way back in 2008. And basically here, a computational basis state is encoding a spatial wave function that is just a product of the orbitals, basically. And so as a result, the symmetry has to explicitly live in the state. So for example, if it's a wave function for fermions, the actual wave function we're simulating on the quantum computer has to be explicitly antisymmetric with respect to particle label exchange. I should say further that the molecular Hamiltonian, it commutes with the particle permutation operator. And so as long as we have made sure that our initial state has the right symmetries, like that the electrons are antisymmetric and that bosonic nuclei are symmetric and this sort of thing, then we can be confident that simulation under that Hamiltonian is going to maintain these symmetries. There's different ways you can symmetrize the initial states, but there's this paper we had from 2017, which gives the best complexity for doing that. The complexity is eta log n log eta, where eta is the number of particles and n is the number of orbitals. This is a very low complexity, so it's always sort of a negligible additive cost to the other things that we might want to do. I'll go through this part especially quickly. In second quantization, we're usually having a number of qubits that's equal to the number of orbitals, and the qubit is just encoding is the orbital occupied or not. And we're able to map the Hamiltonian to qubits usually in a way that gives you local operators. By local here, I mean that the Hamiltonian can be expressed as a sum of a polynomial number of tensor products of Pauli operators. And I think this decomposition into local operators, it's sort of especially Nisky, and that's one reason why people like second quantization, because you can easily measure the terms in this Hamiltonian, or you can simulate just a few of them easily if you like. In second quantization, it's a reasonable use of resources, I think, when you're simulating representations that are near half filling, or when you have a very compact basis. For example, if you're doing a simulation in an active space, it's not a horrible use of resources. So it's sort of very good, I think, for getting a second or static correlation. I should also say that sometimes one might want to prepare states that are not an eigenstate of particle number, like a BCS state or something like that. And in second quantization, as we normally simulate it, you can easily do that. There is some work, though, on performing second quantized simulations actually in a fixed particle number sector, and that in some cases reduces the spatial complexity, but I'm not really going to get into that. Usually, as we use first quantization on a quantum computer, the space complexity is only eta log n, where eta is, again, the number of particles and n is the number of orbitals. And so in terms of the number of orbitals, the number of qubits required is exponentially less than in second quantization. So what we're normally doing here is we have eta different registers, one for each electron, essentially, and it's just encoding in binary which orbital is occupied, hence the eta log n spatial complexity. So in first quantization, the operators, they turn out to be sparse, meaning they have at most a polynomial number of non-zero entries in each row and column, but they're not local. So usually the first quantized operators we can't write as a polynomial number of tensor products of Pauli operators, but they are sparse, which is a general condition that needs to be met for us to be able to simulate them efficiently. Because they're not local, I think that they're not the most Nisky representations, but this doesn't present much problem with in-fault tolerance, as we'll talk about. And so I think that we really ought to be thinking about them there. I'd argue that because the spatial complexity is exponentially better in the number of orbitals, they're sort of ideal for very high precision calculations. You can use a very large number of orbitals. Because you can use a large number of orbitals, you can get away with very simple orbitals like grids or plane waves or something like that. And you end up with very low overhead for, say, including nuclei then in your simulations, because your basis functions don't need to be centered on nuclei. So I think that these are very good for, say, performing simulations of dynamics, but also just because you can use so many orbitals, it's very good for, say, capturing dynamic correlation, which is something that is very inefficient to do from my perspective in second quantization on the quantum computer. So now that we've talked about the quantization, a bit more review here, but we need to talk a little bit about the discretization. So, commonly in chemistry, we use these Galerkin discretizations. They're defined by integrals over the basis sets. These are the most common discretizations, I'd say, in chemistry. There's some nice properties, like the fact that the basis errors are variational from above. They're not sort of compatible with grids in the usual sense, unless by grid you mean something kind of like a sinc function or something like this, because if you were to define the basis as just some sort of discontinuous grid element, then you'd find that all these operators are diagonal. There are some other ways of discretizing things on grids, like finite difference or sort of DVR methods I'll talk about in a bit. But anyways, in second quantization, the Galerkin methods, they give these very familiar forms for the Hamiltonian that I think you've seen before. The space complexity is, again, O of n. Note that I've just written the T and V operators here with these superscripts so that you could easily see what the Hamiltonians look like if you wish to include the nuclei. You just have different masses for the different nuclei, and these alpha and beta would be different charges for the nuclei. But one thing I want to draw your attention to is the sparsity of these operators. And the sparsity is important because in a lot of simulation methods, the cost is proportional to the sparsity. So you can decompose these fermionic operators into a sum of like 8 polystrings, and each polystring is 1 sparse. So you can see that, for example, the Coulomb operator has sparsity n to the 4 in this representation. Now, in first quantization, the operators look similar in a Galerkin discretization, but a little bit different. So you have the same coefficients essentially, but you're writing down the operators now a little different. And I want to draw your attention to this line at the bottom where I'm defining some notation here. Remember, we have 8 different registers, essentially 1 for each electron. And basically the subscript I or subscript J, that's saying which register this is intended to act on. So, for a one-body operator, you're acting on the registers for each electron individually, and you're just having the matrix elements going from Q to P. Then for the two-body operator, you're acting on 2 different electron registers. Now, it might look at first glance like the sparsity is eta times n squared for these one-body operators, but if you think a little bit harder about that, you realize you can actually sort of, group together the terms that all have the same p, let's say, in sort of a one sparse color into the matrix, and so the sparsity here is actually less. The sparsity is only eta times n for the one-body operators, or eta squared times n squared for the two-body operators. And so it would be nice to be able to, implement simulation methods that have that better scaling, because in a lot of cases, eta may be a lot less than n. For example, if you're using a simple basis and you need n to be something very large. Okay, so now I'm going to switch gears to talking a little bit about the methods for how we should think about simulating quantum chemistry, and then I'll connect that back to these representations. So product formulas are great. I think that they can be competitive in a number of cases for simulating chemistry, but at least in the simplest ways of implementing Trotter formulas, the cost is usually scaling linearly in the Hamiltonian sparsity, meaning you just have to sort of simulate every term. There are some better things you can do, but I'm mostly just going to focus on LCU methods because they just sort of fit in better with what I'm talking about. And currently, many of the best scaling methods are LCU methods. So with LCU methods, this is, these linear combination of unitary methods. You write the Hamiltonian as a linear combination of unitaries. And there's a number of different LCU methods, but, one of the versions that I've sort of used most commonly, and I think is very powerful, is this qubitization idea from Guanghao Lo. So, in qubitization, there's sort of a couple implications of the general ideas, but one of them is that you can implement this quantum walk operator I'm calling W fairly simply. And this quantum walk operator, it essentially phases eigenstates of the Hamiltonian with a phase that is proportional to the arc cosine of the eigenvalue. And the way that you create these quantum walks is by a fairly simple looking circuit that involves 2 subroutines, one called select and one called prepare. And what select does is we're going to introduce a sort of ancilla register that indexes the different terms in the Hamiltonian just by a binary value. And what select does is it will just apply one of the unitaries in the linear combination of unitaries to psi controlled on that index register. And then what prepare does is it prepares a special state on that index register, which is weighted by the square root of the coefficients of the linear combination of unitaries. And at this point, the parameter lambda, which is sort of a normalization parameter, has showed up a couple times, both in the definition of what the quantum walk does and also in the definition of prepare. And it turns out to have very significant ramifications for the complexity, so you should pay attention to it. But it's basically like an induced one norm, the sum of the absolute value of the coefficients of the linear combination of unitaries. So one thing that we often want to do when simulating chemical systems on a quantum computer is we want to be able to sample in the eigenbasis of the Hamiltonian, which can be used to, say, prepare eigenstates if we have an approximation to that eigenstate. And so, for example, if you perform phase estimation directly on these qubitized quantum walks, then you can sample in the eigenbasis of the Hamiltonian with a cost that is proportional to the cost of the quantum walk times this parameter lambda divided by epsilon, the target precision. Another thing you might want to do if you want to say simulate dynamics is implement the propagator, which you can do by applying the quantum signal processing techniques, also from Guanghao Lo, to this qubitized quantum walk. And that would have complexity that's scaling like the cost of the quantum walk times lambda times t plus the cost of the quantum walk times a factor that's logarithmic in the inverse precision. So in both cases, the cost is proportional to the cost of the quantum walk times this lambda parameter. Okay, so how does this quantum walk actually scale? Again, we require these two unitaries, select and prepare. And I'm going to give you some examples later on in this talk of how select is realized. For now, I'm just going to say that it's pretty cheap in most cases for chemistry, and that's kind of because the terms in the Hamiltonian tend to have a lot of structure, and it's fairly easy to figure out what term you're supposed to apply just by looking at this index register L. So select is not the tough part, really. And for that reason, I'm just going to wave my hands over it and not focus on it right now and tell you that usually in chemistry, the hard part is implementing prepare. And the next couple minutes here, I'm just going to give some sort of very high level intuition. This isn't meant to be very rigorous, but just to sort of give you a feel of how I think about designing these LCU algorithms for chemistry and how I think about the cost of the prepare part. So the cost to prepare, I mean, the hard part is you sort of have to be able to, in superposition, associate what this coefficient value is with what the index register value is. And so the cost has something to do with sort of computing the Hamiltonian coefficients from an index. And one way that you can do that is by basically just having a database of the different coefficients. And if you do that, then there are these methods which require square root of gamma Toffoli complexity and the square root of gamma ancilla, where gamma is sort of the amount of information needed to specify the Hamiltonian. So gamma is like the size of the database that you would use to look up these coefficients. And so these methods rely on some techniques that were developed in earlier papers for LCU methods of chemistry, which are called coherent alias sampling and QROM. And almost all LCU methods for chemistry use these techniques at this point. So to give some feel for this, if we have the Coulomb operator with n to the 4 terms that look like this, if you sort of take the perspective that this is just n to the 4 sort of random coefficients, and you're not aware of any structure in those coefficients, then you're basically saying that gamma is n to the 4, and you might need a database of size n to the 4. And as a result, you'd end up with an algorithm that's scaling like lambda times the square root of gamma, so lambda times n squared. And so, for example, there was an algorithm that was focusing on cases where the Hamiltonian is sparse that we had a paper about, and it was at QIP last year. I give the archive reference here. But maybe you're more clever than that, and you think that you're aware of the fact that if you sort of write these n to the 4 values of those VPQRS as an n squared by n squared matrix, then that representation is actually low rank. And you can actually write this Coulomb operator as a sum of order n different squared one-body operators. And if you have that realization, then that's equivalent to gamma being only equal to n cubed. And so there's some more recent papers then which use this insight, and when you're using exactly this form, that gives an algorithm that is scaling like n to the 3 halves times lambda. Another form you might consider is if you use a special basis set, then the Coulomb operator has only n squared terms, and that's even further reducing gamma. But if you see Dominic Berry's talk this afternoon, we also recently used these ideas from what's called tensor hypercontraction to show that you can project the molecular orbital basis Hamiltonian into a very slightly larger auxiliary basis, which is non-orthogonal, but which exactly diagonalizes the Coulomb operator. And when you do that, you're then able to get a gamma that's equal to n squared again. And thus we're able to implement quantum walks with complexity that's only complexity order n. Okay, so this is all just to kind of give intuition for how the sort of difficulty of computing Hamiltonian coefficients, or how the information required to specify the Hamiltonian translates into complexity. And you might be thinking about this, and you might say, well, wait a second, I have an idea. those coefficients, I know that they're just integrals over these basis functions. So, maybe I could just compute those integrals on the fly. And these integrals don't have an analytical form, but you can certainly try computing them numerically on the fly using LCU methods. And what I mean by that is you can take this integral and you can break it up into just like a Riemann sum over the integrand. And basically that allows you to rewrite the Coulomb operator as a sum of many, many, many different terms, but each with a very sort of simple coefficient that's just sort of the product of orbitals and 1 over r, basically. Now you've dramatically increased the number of terms in the Hamiltonian, which you might think is bad, but these LCU methods, they don't scale explicitly in the number of terms. So maybe this isn't so bad. And in fact, we have these papers from 2015, which is the first paper looking at LCU methods for chemistry, that explored the idea of doing this. And it maybe almost would have worked kind of well, but it turns out that these approaches are less efficient than you might think. Not because the quantum walk is complex, because they actually give a pretty efficient quantum walk, despite the fact you blow up the number of terms. The issue is that doing this actually explodes the value of lambda. And remember, the cost is proportional to lambda times the cost of the quantum walk. And the reason it blows up lambda is because lambda is the absolute value of the sum of the coefficients. And basically, when you break up the integral into a sum over the integrand, now you're having like a sum over the absolute value of the integrand for many points in the domain. And this is actually a very oscillatory integral. So it turns out that really increases lambda, and it gives you, worse scaling than you would think. But yeah, another idea, which is what I'm really getting at, is, well, how about you just use basis functions where you have analytic integrals? And of course, this is the case for plane waves. So I think most people are familiar with plane waves. They're just these sort of Fourier modes. And in my notation here, omega is like the wavelength, or omega to the 1/3 the wavelength. And Kp is just sort of the wave number. And then these integrals from the Galerkin discretization, they just take this really simple form that I've written at the bottom here. And I'm going to talk about how we use those forms in algorithms in a moment. But first, I just want to step back and, kind of opine about the considerations of using molecular orbitals versus plane waves. So, in second quantization, the molecular orbitals are what give you this Hamiltonian at the end of the 4 terms, but you have a very compact basis, so you don't really need that many, qubits to, represent, say, active spaces in this representation. And these basis functions are centered on nuclei. Now, a couple years ago, I went around giving a bunch of talks saying, oh, everyone should use simpler basis functions like plane waves, because if you use plane waves, you get these Hamiltonians that have much simpler forms, that have only, say, n² terms, and this can lead to simpler algorithms. I also kind of pointed out that the plane waves are often what people are using for periodic materials or for non-molecular or non-Born-Oppenheimer dynamics. So, when simulating crystals, periodic in 3D, or graphene, periodic in 2D, maybe this is what you want. And it turns out that today, essentially, a number of people have, sort of listened to this message, and it's now pretty common in quantum computing today, especially in the more computer sciencey part of the field, to focus on this form of the Hamiltonian. And there's a lot of papers now that are, giving algorithms for simulating quantum chemistry in second quantized plane waves. And sort of all of the best asymptotic scalings are coming from using this form. And I think that's great. I'm sort of glad, people agreed with me. But, I should also say we sort of justified this too by saying that, asymptotically, the basis error in either plane waves or molecular orbitals, it's refined as 1 over n. And so sort of asymptotically, it doesn't really make a difference whether you're using molecular orbitals or plane waves. But there's something a little bit fishy about all of this, to be honest. And, it took me a while to have this really sink in. But the reality is that molecules need just way more plane waves than they need molecular orbitals in order to have reasonable precision. It's at least, I think, 100 times more plane waves than molecular orbitals. But in some cases, you could argue it's even more than that, maybe thousands of times more. So if you needed 100 molecular orbitals or 100 qubits, then the number of plane waves you might need is 10,000 or 100,000. And so you need 10,000 or 100,000 qubits. So even if you have, better asymptotic scaling, the reality is I think that these second quantized plane wave algorithms, and I've written a number of papers on that, But I think that for all but a couple of very special systems, like maybe Jellium, whose molecular orbitals essentially are plane waves, I think that this is very impractical just because it has a very, very large space requirement. I think the number of qubits required for second quantized plane waves is just not very practical. Which brings us to what I really want to convince you is a good idea, and that's simulating these plane wave representations in first quantization. So for simplicity here, I'm just not going to write the U operator, even though in our papers we do focus on simulating that part too. But here's the form of the plane wave T and the plane wave V in first quantization. And it's really a very simple form. So for example, if we focus on the T operator, we see that it's diagonal with this very simple coefficient. The coefficient is just essentially up to some constants. The coefficient is just the square of the integer that's stored in the register that's keeping track of the state. So this is maybe a little complicated. If you're not familiar with LCU methods, you might not follow me here, and that's okay. But the thing that we can do to simulate T in an LCU way is we basically break up this coefficient into a sum or an integral of a bunch of different terms that either have a +1 or a -1 coefficient. And you basically want those +1s and -1s to add up to the correct value of the momentum. And the reason that we're doing it like this is because you can't really change the amplitude of a quantum state and superposition very easily, but you can very easily change the phase of it. And so what you do is you add another register that is like the X register essentially, and you put that in superposition, and then you just you sort of compute the value of the register J squared, and then you ask, is the X register greater or less than that? And if it's greater than that, you phase by -1. If it's less than that, you just phase by 1. And this is an LCU way of basically simulating T, where the prepare is totally trivial and all the cost is in select. And you basically just need to square a number and compute an inequality for each of a number of registers that's equal to the number of electrons. So the whole quantum walk for T has cost of O of eta. So that's very cheap. And if you didn't fully follow that, you can sort of see the paper. But anyways, so the select operation for the V, it's even more straightforward. If you just look at this, all you have to do is basically you have to iterate up to register I. You're going to control the term on I, J, P, Q, and nu, because that's sort of how we're indexing the terms here. And so you're going to iterate up to register I, and then you're going to add to register I nu, which is just a value in a register. So you're just doing an addition. That's very simple. And then you iterate up to register J, and you subtract from it nu. And that's also very simple. And there's eta registers, so this also has cost O of eta. By the way, I might say that if you look at the form of this V operator, the reason it's having this form is because of conservation of linear momentum. Because the plane waves are momentum eigenstates. So basically, if one electron is gaining momentum nu, the other register needs to be losing momentum nu. So as I say, the cost of select for V is very straightforward. It's just O of eta. The trickier part is the prepare for V, where you have to prepare this thing we call the momentum state. Remember, you have to prepare the square root of these coefficients. So you have to prepare a state that looks like this, where nu is taking n different values. And at first glance, you might think that's pretty tricky. I don't have time to go into the details, but in the paper I'm mentioning at the top of the slide here, we show sort of a clever algorithm that actually is able to prepare that state with complexity only O of log n. So the whole quantum walk for this first quantized plane wave representation up to log factors is just scaling like the number of electrons. It's scaling only logarithmically in the number of orbitals. Now, the total cost of qubitization is the cost of the lambda times the quantum walk. So the lambda for T is scaling like eta to the 1/3 n to the 2/3. The lambda for V is scaling like n to the 5/3 n to the 1/3. And so the total algorithm is scaling like eta times the sum of those lambdas, which I've written out here. And you'll notice that this scaling is sublinear in n. It's scaling only like n to the 2/3, which I think is pretty exciting, because That really means we can potentially, especially in a fault-tolerant setting, get away with using a whole lot of plane waves. So maybe you have a concern that 100 plane waves isn't enough, and I think that's a reasonable concern. Well, in that case, use 1,000,000 plane waves. It's not going to cost you that much in terms of qubits. We have only eta log n space complexity, and this gate complexity, it's not even scaling linearly in n. So by the standards of fault-tolerant algorithms, that's not so ridiculous. It turns out that you can actually get even better scaling by doing the simulation of what's called the interaction picture. So there's this paper by Nathan Wiebe and Guanghao Lo, which considers the problem of simulating a Hamiltonian that's the sum of A and B when A has a much larger norm than B. And the general idea is that you can perform this simulation in the rotating frame of A. And then you can use the interaction picture method of quantum dynamics to write down this Dyson series for basically the propagator in this which is the propagator that is sort of being simulated in the rotating frame of A. And it turns out that you can use some quantum simulation methods which are similar to the Taylor series methods of time evolution, but instead to simulate the Dyson series for this expression. And so their result is, to sort of paraphrase roughly, that if C sub B is the cost of the quantum walk for B, like in a qubitized form, and C sub A is the cost of fast forwarding the propagator for A, then the cost of implementing the propagator for A plus B in the interaction picture is roughly going like C sub A plus C sub B times lambda B times T. And what's significant about this is you're not seeing any lambda A appear. It's only appearing logarithmically in the expression. And so if we really wanted to optimize the scaling with respect to the number of orbitals, we could simulate in the rotating frame of the kinetic operator. We can qubitize V in the rotating frame of the kinetic operator, and this would lower the cost to scaling like only the number of plane waves to the 1/3. So just to give you some feel for the numbers, let's think about a simulation that has maybe 50 electrons. So, there have been a number of papers that have looked at the cost of simulating FOMOCO in this, 100 qubit active space with roughly 50 particles. And so, how many plane waves would be required for something similar? Probably a lot. I think 1,000,000 is maybe excessive, but let's just say 1,000,000 is required. Well, eta to the 8/3 and to the 1/3 for these numbers, it's only 3,000,000 here. And the number of qubits would be only 1,000. So 1,000 qubits is more than 100, but you have to realize that those second quantized algorithms scaling as n to the 3rd, which are the best ones we have today, they're still requiring like 10 to the 10 Toffoli gates, which is so many Toffoli gates, you need to have multiple factories for distillation. And so you end up needing a lot more physical qubits anyways. And so this isn't really a ridiculous number of qubits. And, roughly n to the 3 is about 1,000,000 if you're looking at 100 molecular orbitals in second quantization. So these costs at a glance, they look comparable. But if we want to get even higher precision, remember that the cost of suppressing basis error is the basis error is proportional to essentially 1/n. And so because we now have a method that's scaling like n to the 1/3, we can now approach the continuum limit with gate complexity that's only like 1/epsilon to the 1/3, which is a big improvement over what we had before of 1/epsilon squared. It's an epsilon to the 6 improvement. So I should say that, that paper was published a couple years ago, and my team has been working on compiling these algorithms to sort of explicit circuits, explicit fault-tolerant circuits more recently. And what I'm actually showing here is some data that's a little bit out of date. These numbers are about an order of magnitude worse than where we are today, but I didn't have better figures, so regardless. Basically, this first plot in the upper left, I'm showing this is for 100 electrons. In the interaction picture, I'm showing the number of Toffolies required as a function of the number of plane waves. And I'm plotting it for a couple different values of the Wigner-Seitz radius, basically the density of the electrons, because that scales the lambda parameter. And you can see maybe like a reasonable Wigner-Seitz radius to look at is the blue or the green. You can see there's, the number of Toffelees isn't small. It's like 10 to the 16. That's kind of where the molecular orbital algorithms were a few years ago. On this other plot, the number of plane waves is fixed on the right of it. The number of plane waves is fixed at 100,000, and I'm showing the cost as a function of the number of electrons.
5 minutes.
Okay, yeah, thanks, Nathan. So it turns out, though, that on the bottom here, I'm showing the same things, but for the cubitized algorithm. And while the cubitized algorithm, it has quadratically worse scaling in the number of orbitals. It's scaling like n to the 2/3 instead of n to the 1/3. And n is very large. It turns out that the interaction picture algorithm, there's sort of a lot of overheads associated with simulating this Dyson series. And so the cubitized algorithm for the regimes of interest is actually turning out it's a bit better. And so you could see that, maybe between 10 to the 10 and 10 to the 11 Toffelees were pretty competitive for systems with, say, 50 to 100 electrons and 1 million plane waves. And so I think that should probably be compared to these sort of estimates for computing Tomoko on a molecular orbital basis that are also requiring about that same number of Toffelees. So this radically different approach in first quantization is actually quite competitive with the molecular orbital approaches. And we'll be publishing a paper about this in a couple months, and we'll be giving a lot more details. I think the paper is at about 90 pages at this point, so you'll have plenty of details. Okay, so I'm maybe going to skip through this pretty quickly, but I should say that, a long time ago, people proposed that, just do a first quantized simulation in a grid. And that seems kind of simple. And you could kind of write down a Hamiltonian that looks like this. And, really, there's nothing that's too wrong with that. You could use that representation. It's not a Galerkin discretization, but that's not that big a deal. And, these previous papers, they used Trotter, and their Trotter steps had eta squared complexity, which is worse than the cost of our quantum walks. But the number of Trotter steps required, at least for that paper, were fairly high. Wasn't really competitive with some of the other methods. But one could imagine doing these simulations with a very high order Trotter formula and probably doing okay. So I'm just going to kind of skip through some of this. The point is, though, that you could cubitize these grids. And this hasn't been published in any paper, but I'm just telling you, it's very straightforward to argue that you could cubitize a simulation on these grids and get exactly the same complexity as we were able to get in cubitizing the plane wave representation. And I have reason to think that the constant factors in cubitizing the plane wave algorithm will be a bit better, although it would be nice to work it out for the grids. I just happen to kind of like the plane waves better. But the point is, the grids and the plane waves, they're kind of the same. You can cubitize both in first quantization and get good scaling. Okay, so with that, I'm going to sort of conclude here and just sort of reiterate that I believe the long-term future of quantum algorithms for chemistry is first quantized. We're down to n to the 3, where n is the number of orbitals, gate complexity for molecular orbital calculations. And I think that that's getting pretty optimal. I don't think we're going to see that improve much. But I don't think that complexity is going to scale to treating the computational cells of real materials. If you want to treat, say, a metal oxide or something, you're needing to have potentially thousands of molecular, a few thousand molecular orbitals, and this is getting very, very costly. And on the other hand, these second quantized plane wave algorithms, which years ago I was sort of suggesting, I think they were a step in the right direction, but I think that they're ultimately pretty impractical for chemistry just due to the space requirements, because you're going to need so many plane waves. I do think it's a really beautiful advantage of the plane wave approach is that we don't need to worry about the mess of computing active spaces anymore. I mean, that's something which really requires a lot of chemical expertise, I think, to do well. And with plane waves, it's just a simple basis. You just set up the calculation and use a bunch of them. Of course, you might want to use pseudo potentials in some cases to reduce the number of particles, and that is compatible with these methods. So the other thing is that within first quantized plane waves, non-Born-Oppenheimer calculations are almost as cheap as Born-Oppenheimer ones. There's very little additive cost to treating the nuclei. And the reason for that is because you tend to have more electrons than nuclei. And so adding the nuclei isn't even sort of doubling the number of particles, far less than that typically. Since the basis functions aren't treated on nuclei, there's no real complication to doing this. And thus you can very easily do dynamics. You can get, these reactive scattering coefficients. You can, actually do the sort of this fluctuation dissipation theorem things, or compute these, flux side correlation functions to get exact rate constants. You can compute, non-equilibrium properties, watching how these ensembles relaxed equilibrium and that kind of thing. Again, we've dramatically improved the gate complexity to simulate within epsilon of the continuum, to the point where I think what we call spectroscopic accuracy, which is, 3 orders of magnitude below chemical accuracy, is now achievable within the basis. We're going to quickly run into the limits of relativistic effects, but there are ways of treating those relativistic effects. And, if we really want high precision, we could get there. An open question in my mind that I think is a very important question for the field is, we've now been able to reduce the complexity so that we have scaling like 1 over epsilon to the 1/3. But I wonder, is it possible in any way to get down to scaling that's polylogarithmic in 1 over epsilon, which would be an exponential improvement in the rate at which we approach the continuum? And I don't see any fundamental reason why not. But I don't really know how exactly to do it, unfortunately. So for me, that's sort of an open question. Another question is it possible to implement first quantized Trotter simulations with costed sublinear in N? And I do know the answer to this. The answer is yes. And basically, you can use these Trotter steps that are coming from, say, this earlier work by Casal that have eta squared complexity. And you might be able to combine them with fast multipole methods or something like that to get something like O of eta complexity. And then you can use the Trotter analysis that is coming from these more recent papers that focused on second quantization from, say, Earl Campbell and Yuan Su and others. And I think that those can be adapted to first quantization and can give a number of Trotter steps, which is scaling sublinearly in N, although from when I've looked into it, I think that the scaling will still be worse than the cubitized plane wave algorithms. So anyways, stay tuned for upcoming resource estimates, because I've been working on this with Dominic, Nathan, and Yuan Su for a long time, and we have a paper that's coming out on this. But this is all I had time to share today. So thanks for your time.
All right, wonderful. Thank you very much, Ryan. So let's open up the questions. Lucas Vischer asks, in a first quantized future, how are organic chemists going to interpret reaction mechanisms done to a large extent in a linear combination of atomic orbitals conceptual framework?
Yeah, that's a good question. I mean, one thing that you can always do is that you can project atomic orbitals into a plane wave basis. And if you're using, 1 million plane waves, it's not going to be perfect. But for the purposes of the intuition of an organic chemist, I think that, a molecular orbital projected into 1 million plane waves an atomic orbital projected into 1 million plane waves is still roughly an atomic orbital. And if you do that, you can then just apply these Givens rotation techniques to rotate from the basis of plane waves into this basis of atomic orbitals that are projected into plane waves. And you can then, measure the system in that basis and get some intuition for what's going on.
All right. Any other questions for people? All right. Well, if there's no questions, then Ryan, I'll grill you for a bit. So you mentioned the possibility of running into the spectroscopic for trying to get spectroscopic accuracy. One of the main limits that we run into is relativity, and dealing with relativity properly requires going over to a quantum electrodynamics framework. So one of the questions I guess I have is, what would the challenges be of representing quantum electrodynamics from a first quantized perspective?
Well, I should say that there's sort of a spectrum of ways you could treat relativistic effects, and going, full Dirac equation, for example, is probably one of the more extreme versions. But I assume that's kind of more what you're asking about. So if you did that, I mean, the first thing that sort of comes to mind is that the way we typically implement first quantization right now, it tends to fix us in a certain particle number manifold. Whereas I guess in sort of a Dirac equation picture, you could have, you might not want to be in that manifold, right? I think you can have particles sort of coming out of the vacuum, although I'm really not an expert on this. So I would think, though, that that one should be able to adapt first quantization so that you could allow like a number of particles that's greater than eta, but is still something reasonable. Like, you might expect that at any one point you're going to have contributions up to like 2 eta, or, I'm really not an expert in this, but maybe something like that. And if you were able to make such a restriction safely, then you could still have space complexity that's asymptotically eta times the log of n. However, if you really had to go up to, a number of particles that's going all the way up to n, then you're in trouble. But I don't see that seems pretty far-fetched that would be the case. So there's definitely some more work there. I mean, I'm sure that, it's a different, there are different operators you're going to have to simulate in the Dirac equation. And I think it would be a really fun problem, but I haven't thought too deeply about it.
Cool. Any other quick questions from the audience?
Yeah, I have one quick question. When you showed the number of Toffolies that you need with respect to the number of orbitals, there were a kind of discontinuous jump at some point. Is there any reason for that?
Yeah. So the reason, actually, Nathan probably knows the reason for that more than me, because I think he's been working on the part of that algorithm that gives that. But I think that what's going on is that basically currently the way we're implementing things, there's part of like the state preparation, which is working especially well when certain numbers are like powers of 2. And that procedure could probably be adapted to work away from powers of 2 so that you get smoother curves. But for the purposes of just sort of upper bounding the cost of the algorithm, I think we just have been kind of lazy and haven't done that. But yeah, Nathan, you may be able to.
The other matter that ends up coming in is that when you were looking at the truncated Dyson series, and in particular, there's discretizations that end up coming in with the value of k that we end up picking. And that's one of the things, at least for the interaction plot on the top, that leads to some of the big jumps. With cubitization, it's entirely these powers of 2 issues that Ryan's talking about that end up leading to this. So when we end up hitting these thresholds, then we have to go to a larger circuit, and we see a discontinuous jump. There's ways we could smooth those out, but it's not clear we would really strongly benefit from doing that.
Okay, thanks a lot.
No problem.